Hello everyone, my name is Farhan and I'm a PhD student at School of Computer Science and IT, University College Cork, and I'm doing my PhD in the supervision of Professor Jared Bish. Today I'm going to talk about an approach for optimal base station selection in 5G heterogeneous network for smart factories. So to begin with, this is my presentation outline. So we'll start with the introduction and the research problem. So in introduction, we'll look at how 5G wireless network plays an important role for cyber physical manufacturing system in future smart factory. We know that the 5G communication standard envisions three main categories, namely the ultra reliable low latency communication, enhanced mobile broadband, and massive machine time communication. Uh, with the availability of the equipment, 5G based heterogeneous networks in smart manufacturing support Industry 4.0 use cases, as we know that they offer very high speed connectivity with reliable communication. Also, the attractiveness of the wireless mobile networks for manufacturing is mainly due to their straightforward deployment and mobility support for a wide range of industrial environments. Uh, also, data traffic in these smart factories is normally generated by a combination of a short range indoor wireless devices and long range outdoor users with varying mobility patterns. So, to cater this, normally the multicellular wireless networks are well known solutions incorporating the deployments of small base stations such as the Pico or Femto cells along with the macro base stations. Uh, and on our current scenario, we're going to see the deployment of these heterogeneous networks in the methodology and system model part as we'll move forward in the presentation. Uh, and and the problem we are actually looking here is of the best base station association strategy in HetNet's deployment, which is the we're going to discuss in this as we move forward. And after that, we're going to see we'll discuss the depth of the subject in the results and discussion part. And lastly, my presentation will discuss about the future work, that what we plan to do in future. So in the introduction, uh, the 5G based heterogeneous network HETNETs uh, have been attracting interest recently to support manufacturing processes in smart factory use cases. Smart factories, require high performing wireless systems with high data rates and improved spectral efficiency to support mobile robots and other autonomous vehicles. And to provide low latency, high coverage 5G deployments comprise of multi-tier femto-pico macro cell networks, and they are seen as a quite a possible solution which to meet the requirements, particularly of the data rate requirements. So uh, so so this work mainly analyzed the impact of the base stations association strategies such as the maximum receive power and maximum signal to interference plus noise ratio signer for a 5G heterogeneous network for low mobility robots and high mobility autonomous grounded vehicle in conjunction with the fixed wireless sensor devices. So, so in our main scenario, we are going to discuss about the two base association strategies and and their impact on the high mobility and the low mobility autonomous vehicles. Uh, so the research problem mainly compromise of deployment of base stations, um, but in an optimal as we know that the deployment of the base station in optimal location is normally is a very challenging optimization problem. But but in this scenario, there is another key question, which is the optimal selection of the servicing base station. That, for example, which user equipment is going to be served by which cell. So this also depends on the number of parameters which we're going to look into in our coming slides. But and the allocation and the provision of the network resources for different type of devices in a smart factory is also one of a challenging problem, and the best base station association strategy in HETNets are currently still being investigated and is normally compared with the classical Max Signer approach, uh, which simply means that the user will get the servicing base station which has the maximum signer approach. But uh, but here we are going to make a comparison between the classical max signer approach and the maximum receive power approach. So I'm going to explain these two approaches in our coming slides. So this is a typical 5G cellular network having a smart factory. So you can see this is a typical urban environment, and this is our smart factory, the point of focus, and you can see that we can find these kind of IoT and autonomous devices and sensors in a typical smart factory, and their connectivity with the macro base stations, with the pico base stations, and the femto base stations, and the key question here is that which device is going to be docked on which base station, or which base station is going to be the servicing downlink node for which device, and it depends on the number of parameters: the RF environment, the path loss, and the received signal strength, the RSSI index we call it. So the methodology here is very the conventional one. In order to study the resource allocation problem, we consider a scenario where different wireless devices are embedded in an assembly line. You can see that in our in our scenario, and our network mainly consists of the macro, femto, and pico base stations, and which with and they all are having the operating in CISO mode, which is the single input single output mode, and with a single transmit antenna. So we are not using MIMO currently in this case, and this user equipment includes the low mobility IoT devices and high mobility devices, or vehicles or robots, and high mobility autonomous mobile robots are served by the picocells for optimal coverage and performance, and you can see that that's why the picocells are deployed in a close proximity to the conveyor belt. So you can see that the picocells are being deployed in a close proximity to the conveyor belt, and that is deliberately placed there in a predefined position in order to minimize the path loss, in order to give the better and smooth receive signal strength to the respective devices, and in order to improve the network parameters and minimizing the RF noise. In our system model, the stationary IoT devices use user equipment with limited mobility are served either by the nearby macro or femto base stations, depending on the proximity, and the user equipment and the femto base stations are we're using the Poisson point distribution for their deployment, whereas the macro and pico base stations are distributed using the predefined positions. So and the cell association strategy actually decides at which parameter is used to make the base station association decision, and few parameters like the antenna height and the power of the transmit antenna is given. For example, the macro base station antenna is 25 meter in height and the transmit power of 40 watt, whereas the pico base station obviously has a less height of say 5 meter with a transmit power of 2 watt, and femto base station has a height of 1.5 meter with a low transmit power of 0.1 volt. So coming back to the cell association strategy, so in order to exploit this heterogeneous cell architecture, we are going to investigate these two different cell association strategies, which is the maximum receive power and the maximum signer, and the cell association strategies. Talking about the maximum signer association strategy, you can see that maximum signer association strategy devices are connected with the base station simply that offers the best downlink signer, and which means that each user is attached to the base station for which it has some preliminary highest signer. So and the preliminary signer is actually the signer which is calculated after the total path loss and the base station transmit power and antenna gain and noise power. So it's a total of all these things. You can see in this this diagram corresponds to the scenario diagram of a smart factory where we place the macro base station in the blue in the predefined positions and the pico base stations in the green and the respective user attached to them. These pink ones are the pico base station users, whereas the red one shows the macro user equipment which are being serviced by the macro base stations. And the other cell association strategy, which is the maximum received power. In this cell association strategy, each user is attached to the base station for which it has the highest received power. So this particular strategy is based on the power rather the signer in on the other hand. So and the receive power is a power received after the total path loss, base station transmit power, and the antenna gain. So more or less the you can see that the deployment and the cell association is kind of similar to what we see in the previous slide. But let us come to the results and discussion part. So you can see there in this very interestingly in this graph that it shows the empirical ECDF cumulative distribution function of the average user signer for maximum receive power as well as the maximum signer, and you can see that the performance of the maximum receive power is moderately better than the maximum signer. Also, if we move towards, we have plotted the ECDF of the throughput for the same scenario for both cell association strategies. So you can see that the maximum receive power base station association strategy shows improvement in terms of the average user throughput over the maximum signer cell association strategy. So finally we come to the conclusion part. So you can see that this work actually analyzed the impact of two different base stations association approaches, namely maximum signal to interference plus noise ratio and the maximum receive power for 5G heterogeneous networks base station deployment in a smart factory. We saw that empirical CDF of the average user throughput and the user signer for each cell association strategy for the given scenario was plotted, and the experimental results mainly showed that our deployment scheme combined with the maximum receive power selection strategy outperforms the maximum signal to interference plus noise ratio cell association strategy. And if we compare the user throughput and the user signer of the both strategies for our scenario, it is evident that the maximum receive power is an optimal technique for base station selection in 5G heterogeneous network for smart factories. Coming back to the last part of our presentation, which is the future work. So in future, we actually aim to investigate the effect of different scheduling algorithms combined with these cell association strategies, which we have discussed. And also we plan to see the effects of densification of femtocells in our previous work. So the densification means when we increase the number of femtocells and we densify the network with femtocells. We also plan to analyze the effect of different parameters such as the transmit power, cell densification, placement of small cells, and MIMO. And the one other thing is that we are also interested to look into the uplink aspect of the current scenario, and also we would be interested in to see the and utilize the device-to-device communication, D2D communication, to enable the relaying between users in order to improve the coverage in a smart manufacturing factory. And lastly, we are going to investigate the impact of interference between two robots, machines, and mainly the interference due to the high emissions of the OFDM and the effective interference mitigation. So that's what we plan to do in future. So out of this work, we have submitted our article in IEEE WOWMOM 2020 in PhD forum, and the article is under review currently. Thank you very much, and if you have any questions, you may post it below the video, or you can contact me with via my email address, which is farhan.khan@cs.ucc.ie. Thank you very much for watching.